one of them is the performance of every one of them is very close to synchrotron techniques. Like for example, we have a micro XRF system that can measure things in sub ppm level. And that is used by a lot of customers, like in the semiconductor side, when they are looking at atomic layer deposition or trace level. And we can go all the way down to all those carbon, oxygen, nitrogen that SCM cannot do because uh, they are in trace concentration. We also have an X-ray absorption spectroscopy that uh, look at the valence state, for example, whether it's iron 2 or iron 3 plus, or look at bond length. And then today we're going to concentrate on this product called Eclipse. Eclipse X-ray microscope is the highest resolution X-ray microscope in the market right now. So why I'm going to explain to you why you need high resolution or highest resolution you can get, especially when you are trying to do shale and tight sands. And then we have also another X-ray product, but we are not going to talk about that. So today we're going to focus more on X-ray microscopy. So to start from the beginning, what is X-ray microscopy or computed tomography? What it does is that if you put an X-ray source and you put your rock next to the source, so therefore the X-ray source will project that image like a slide projector onto a detector or a screen. So this is what you do is that when you just do a single projection, it is a 2D image. This 2D image looks like this. This means one slice will look like this. Now you rotate the sample and then rotate maybe 1/4 of a degree, and then you get another slice. And then you rotate again, you get another slice. Imagine if you rotate 360 degrees, maybe 360 degrees every 1/4 of an angle or every half a degree, you project an image. So eventually you get maybe hundreds of 2D projection. So when you get all this, what you do is that you have a software called tomography reconstruction software. So what the reconstruction software do is it will create a 3D data set or 3D image. So once you have a 3D image, now you have a virtual three-dimensional image that you can now slice in different direction. I can slice from the top, I can slice from the side. So it will give you slices just like what you see in your SCM. In SCM, you have to polish your sample, right? To do the 2D image. But in tomography, because it is non-destructive, I don't have to polish. I just have to put my rock and then I now do I can electronically or digitally, I can section them. So I can get the second slice. Okay, I can get more and more slices that way. So that will be what we call tomography or CT scanner, or they also call X-ray microscopy. So like for example, if let's say let's say I have a catalyst or I can have a rock or whatever, you now do this on the SCM, right? You polish this section, then you can see that, oh, this is the bright area, therefore is higher atomic number. Yeah, dark area, this means you may have void, right? And in between, then you have different density. So SEM just give you a single slice. But in tomography, after I've captured the whole 3D volume, now I can cut through the sample like this. And then you can see that I can, just like I'm slicing it physically, I'm now slicing this sample electronically. So I can see the bright thing, which are the higher Z element. I can see all the cracks, right? and then I can see the voice, I can see different density material. So in your SEM, you can only capture one. But what you are seeing is that now we can capture the whole volume. Let's say in the oil and gas, they normally work with a core. Like for example, you may have a 40 millimeter core, you may have a 10 millimeter core, you may have a 1 millimeter core, depending on what resolution you want. But then once you capture this 3D image, you can do that at different resolution, and therefore you can create the report for your customer. Now, to start with tomography, we have to understand a term called Voxer. Voxer is actually volume resolution. What is the resolution of the volume? For instance, how do you get magnification? If I bring my sample very close to the X-ray source, then I have higher magnification. If I bring my sample further away from X-ray source, then you have lower magnification. It's just like your slide projector. How do you get the bigger magnification on the screen? You bring your sample in the slide projector side, you bring your sample further away from the screen, you get higher magnification. You bring your slide projector nearer to the screen, then you have lower geometric magnification. So X-ray microscope or tomography works on the same principle, except that now if I bring my sample closer and closer to the X-ray source, now I have higher magnification, and this magnification is called geometric magnification. Geometric magnification is just this distance to this sample divided divided by, this is DSS, right? To be the total distance. This means the total distance is distance to the sample plus distance to the detector uh, divided by the distance to the sample. So that gives you a magnification factor. Now, how do you get the 3D volume is this? Because your sample, when I just do one projection, I will only have a 2D image. And what is the resolution of the 2D image? Depending on the resolution of your detector. So your detector can be so many megapixel. The bigger the megapixel, like 1K by 1K, or 2K by 2K, or 3K by 3K. So those are the megapixel of your detector. And how do you get the voxer? Is when you rotate the sample and you reconstruct it, now you can create what you call a 3D volume. So let's say my detector is 1000 by 1000. So therefore, your voxer will have 1000 pixel here, 1000 pixel there. And therefore, one of the pixel is called a voxer. All right. So you can see that, okay, the voxer is actually what is the detector pixel size divided by your geometric magnification. But if that's the case, then the people will think that, okay, let's see if I can cheat. Now, if I were to bring my, let's say my sample as close as possible to my X-ray source, then you will get higher magnification. But the problem is this. You can see that if my X-ray source or my X-ray tube, that means the spot size of the X-ray tube is big. So in other words, when it's big, when you bring two objects near together, this source will create what you call a penumbra or the blurring, right? Just like when you have the eclipse of the sun or eclipse of the moon, you have the shadow. So therefore, two objects, when they are brought together, so you get the penumbra or the blurring effect. So in other words, if my X-ray source is 5 micron, I will never be able to get resolution better than 5 micron. You understand that? If my X-ray source is, let's say you want to have submicron resolution, can you have a 5 micron X-ray source, X-ray spot size to get that? The penumbra effect will say that no, it cannot be better than the size of your X-ray tube, the size of the spot size of the X-ray tube. So this is one basic principle about the spot size of the X-ray tube will determine or limit your resolution. So if you want to do shale analysis, you will have to get something that is submicron. And that way you will be able to see more things. So what is this thing that we are talking about? That if my spot size is very if my spot size is big, so what will happen? You will see that you have this shadow at the edge, and that will limit your resolution. So therefore, now we ask a question. You have a problem, and your problem is that your sample has very small spot size. If you are dealing with shale, you're dealing with tight sands, you're dealing with carbonates, you will need to have submicron resolution. So what are the techniques that you can create in your X-ray microscope or the micro CT in order to achieve submicron? So if you take a look at this particular uh, at this particular formula, you see that the spatial resolution is a function on your spot size of your X-ray tube, and then there's a geometric magnification, and then there's also a function on the detector pixel size. So this means the detector resolution and the spot size of your X-ray tube determines your final spatial resolution. So my question is that if you're going to make a micro CT or you want to make an X-ray microscope, how do you get submicron resolution? There are actually two techniques. The first technique is this, like what I've shown you earlier. You need to have a submicron X source spot size in your X-ray tube. That means your X-ray tube must be a nano focus tube, meaning that the spot size of the nano focus tube must be less than 1 micron. Then secondly, if you have a very small spot size tube, your detector, your flat panel do not need to be very small spot size. You can be maybe 50 microns or 30 microns is fine. You still will be able to reach submicron. Okay. And why the spot size is important? If your X-ray source spot size is 5 micron, you will have a penumbra, which will be the size of your tube source. If you have a smaller spot size, then the penumbra is smaller. If you have a very tiny nano focus tube, like a few hundred nanometers, then your penumbra will be very little. So therefore, you can get this resolution almost the same as your spot size of your X-ray tube. I hope I made myself clear there. All right. So in the product that we're going to discuss with you today, we have a X-ray source spot size that is less than 300 nanometer, and therefore our spatial resolution is 300 nanometer. So let's take a look at the second way you can have a submicron spatial resolution is using another technique, using an optical microscope lens in front of your detector. So this is what you call a two-stage magnification system. And this is the technique that we borrow from the synchrotron when we started X-Radio, and now it is our product is acquired by Carl Zeiss, and they have a the name they call it Versa and so on. So anyway, in this two-stage magnification technique, like X-radio or Zeiss, you don't need to have a very small X-ray tube, a small spot size X-ray tube. You can get an X-ray tube that has a spot size of a few micron. In this case, they use a dish X-ray tube which has a few microns, but then the detector side has to be submicron. So if this detector here is submicron, you can have a spot size that is larger, so you can still get submicron. So therefore, when we were doing X-radio, this is what we did. We have a detector, and then we put a lens, an optical lens, like your visible or optical microscope lens, like your 4x, your 10x, your 20x, right? And then in front of the optical microscope lens, we glue in a scintillator in front. So this one is a scintillator in front. Why scintillator? Because the X-ray absorption is going to hit the scintillator like what you see in your TEM. Your TEM, how do you get the image? The image is the shadow or the contrast of the image goes on the phosphor screen on your TEM. So here you put a scintillator in front of your objective microscope lens. So with that, now you'll be able to see contrast or the projected image on the scintillator that is now magnified onto the detector. So let's take a look. This is the way we used to do that. An X-ray source. Then you put in your sample. It can be a PCB board. It can be a rock. It can be a plant. It doesn't matter. Then you have a scintillator. You have an objective lens. Then you have a CCD detector. So that will be the second way. How do you get the second way? That means you have a spot size instead of submicron. Now you have a few micron spot size, and the detector now needs to be submicron. How do you get this detector to be submicron when the CCD detector that we used to use is 13 micron pixel? So 13 micron pixel, in order to get you submicron, will require that you need a magnification. Let's say if I use a 10x magnification, now my effective pixel size will become 13 divided by 10 is 1.3. So it's 1.3. Now, what if I use a 20x detector? That means now your 20x detector will be 13 divided by 20 is 0.65. What if I now use 40x detector? Then you divide by 40, your effective pixel size is 0.32 micron. So 0.32 micron you can is only the voxel size. It is not the spatial resolution. So you need at least 2 pixels to make the spatial resolution, and therefore the best you can normally do is about 0.5 micron. So that is how Zeiss does it. That's how X-radio we originally did that. And now this is what happens with the scintillator, objective scintillator architecture. If you were to use this technique, what are the challenges? The challenges is that if you want to do very high resolution, you're going to have a lot of problem. What is the problem? Is that if you use objective like 20x or 40x, your system must be coupled to a very thin scintillator. That is one issue I'm going to show you in a moment. And the second thing is with this particular system, uh, the cost of the replacement of the X-ray tube, because they use a seal tube, they If anything goes wrong, you have to change the whole tube. And that has to be replaced every few thousand hours. And in other words, you may have to change your X-ray tube every maybe every 1 or 2 years, and that may cost up to 100,000 US dollar. So that is a problem for many laboratories because of the high cost of those X-ray tubes, and also because of the objective lens that is the problem. When you are doing, let's say, 20x or 40x in that system. So what does that mean, right? Every objective microscope in your visible microscope that you use in your lab, you have what you call a depth of field or depth of focus, right? There is only a narrow range depending on what is the magnification. If I have a lower X, my field of view or my depth of field is very large. But let's say if you start to go into 10x, then your field of view, where things are in focus, is smaller. If you go to 20x, the field of view or depth of field is even smaller. 40x is very, very small. So in other words, if you look at something like this, if I have a CCD camera, I have an objective microscope. Now I'm using this objective microscope, let's say 10x. 10x, my depth of focus is 8.5 micron. So in other words, you have to make a scintillator that is about 8.5 micron thick. Now, if you say that I want a 40x so that I can get the 0.32 pixel, 0.32 micron pixel. So the physics says that your scintillator must now be thin up to 1 micron. Now, what's wrong with the very thin scintillator? Your efficiency. So your scintillator has to convert the X-ray into visible light. So if it's thicker, now you stop more X-ray, then you have more contrast. But then if it's very thin, most of the X-ray energy will go right through the thin scintillator and it doesn't fluorescence. So in other words, you do not have much detector, much signal or much sensitivity with the 40x. That's the reason why most customers that have got the Zeiss systems or the X-ray systems, they do not use the 40x for real samples. They normally use the 40x only for calibration. That means to show whether the machine can give you zero point 0.5 micron resolution. So it is not normally used for real samples like rock samples. It will, unless you have to thin your sample until it is a few micron. Otherwise, you do not normally use the 40x to do your work. So that is the drawback, is because it is very inefficient at the higher objective lens. And that's also the reason why you cannot use 50x. If 40x you cannot use, 50x you thought that you have higher magnification, but then it's not usable because your scintillator can even get even smaller. Or 100x. 100x is impossible using this technique. So these are the two techniques. You have a very small nano focus tube that is a few hundred nanometers, then you can get submicron spatial resolution, or you have a big spot size, but the detector has to be very small. But in this case, you have to use optical microscope lenses coupled with a thin scintillator. So these are the things that that you have to be concerned about. And then the other thing is that one of the advantage of the Sigray system is that we use a unique open source tube that allow you to be able to operate the system for 4,000 hours without changing the filament. And the replacement cost is only a few $1,000s. Whereas the seal tube, like from the Zeiss or the X-Radius, you replace it, it will cost 80 to $100,000. So that is a lot of money for a lab. You can buy many equipment for that. So that will be one of the drawback I want you to know. And then Sigray also have very high resolution detector that allow us to get high efficiency as well as high resolution. So what is the Eclipse advantage? 300 nanometers spatial resolution. This means you can get down to maybe 100 nanometer or 150 nanometer voxel size. And then next, we also have options to put in the second tube. We have options to increase your field of view. We have also robotic handler, and also our tomography can be helical. That means if you have a long cylinder like a rock, you can do a scanning that's helical. Or if you have a big flat sample, we can do an offset. And this one has a low cost of ownership, right? Because of the X-ray tube, which is not a seal tube, but then we have an open tube. In other words, when there's something wrong, you want to change the filament, the customer can do himself, or you want to change the target, it can also be done, right? All right, so these are the resolution target that we can easily see zero point 0.3 micron or 300 nanometers. And also, your system can give you an option to have 200 nanometer spatial resolution. That is, if you need to do shale, now you may have a nano X-ray microscope uh, uh, that is also allow you to look at things like the bigger samples like the carbonates and your sandstones or your tight sands. So here's the advantage of what's the difference between an X-ray microscope that is zero point 0.5 micron versus what you can get at zero point 0.3. You can see the images are a lot sharper and the contrast is better. And this is helical imaging. This means if you have a long core, like what you do in oil and gas, now your scanning is in a spiral or in a helical manner. You can also have, let's say you have a wide sample, we can scan on one side and then scan on the other side so that now you can actually stitch the two samples together. So let's take a look at the digital rock physics. In digital rock physics, most people start out with sandstone in order to understand permeability, resistivity, elastic property, and most of the time, the data that is obtained from digital rock physics for sandstone, because the pores are pretty big, it actually correlate pretty well with the porosity and the grain size and texture. So for if you want to do digital rock physics for sandstone, you can buy a ordinary micro CT that has 1 micron resolution. You are still okay with that. But then, uh, when you're going to deal with carbonates, it is going to be a problem. Why carbonates is a problem? Because carbonates have big voids or big pores, right? Sometimes millimeters, or sometimes several hundred micron, and all the way to nanoscale pores. So therefore, you cannot just use a cheap micro CT or X-ray microscope. You need to have a much higher resolution system. So a lot of times you might also need to look into the SEM for the nanoscale type of pores to go into your digital rock physics. So it requires higher resolution system. So now what I want to show you is this. if you have a range of products starting from sandstone, sandstones have pore size all the way up to maybe maybe a micron or so, right? Carbonates will have a spot size. Let me see. Let's see here. I'm not sure whether you can see. Okay, can you see it? Yeah. So carbonates, are you still on the screen?
Yes, yes.
Yes,
Okay.
Mr.
Okay.
Yes.
Yeah. So carbonates will have a pore size range from big microns all the way down to nanoscale. Whereas shale, you have pretty small pores all the way down to nanoscale. So if you want to take a look at how do you characterize these things. Now, if you say that, okay, I start with a 100 millimeter core, that one cannot be done in a micro CT. You normally use a medical CT scanner to do the core, to image your 100 millimeter core. But then after you have inspected that, then you do a sampling in your big core. And then from there, you can start using your micro CT or the X-ray microscope. So you can see that the range of the eclipse system will be able to cover you all the way down to your uh, here. It covers all the way down to your let's say your 300 nanometers here. So this means you will be able to cover a full range, covering the carbonates and covering shale for most of it. And if you want to go down further, you can go down another 100 nanometers to 200 nanometers as an option. Or at this stage, you may have to physically do a slice in your SEM and give more information regarding the final pore size for your shell. So that will be the normal workflow that people do with digital rock physics. So in digital rock physics for enhanced oil recovery, so you will look into things like viscosity, density, and so on, and the drainage, the relative permeability, and the water saturation. So therefore, most of this type of work is done with the X-ray microscope, where you will model the flow of water, oil, and gas on the rock in three-dimensional form. Okay, why is all these things very important in rock physics? Let's say if you have a microscope or X-ray microscope or a micro CT that has a resolution of 3 microns or 1 micron or whatever versus another one that is zero point 0.5 micron. You can see that if I capture an image, like for example, if I do a thin slice, right? And if I were to just do a image capture, if my resolution is not good enough, what happens is that I will not be able to look at the very sharp edges at the pore size. If your resolution of your system is 1 to 3 micron, you find that all the sharp edges at the interface of your grain will be rounded out. So if let's say your model shows that your pore space is rounded out, therefore what will happen to your flow? Your prediction from the flow will say that, oh, it's good permeability. because there's no friction at the edge like here. But how can you capture this edge? You need to have a much higher resolution system that will be able to capture the edge between the grain boundary. So that is the reason why you will need to have as high a resolution for your X-ray microscope to get the accurate prediction of permeability. Right. So now back to your shale. How do you do shale analysis? A lot of times you can do your micro CT, and ultimately you may also have to rely on the physical cross section from your SEM or your FIP in order to predict your model, right? Micro CT, even if you go down to 200 nanometers, is still not enough to capture all the pore size. You need the SEM or a FIP to go down to maybe a few nanometers. So therefore, you just need to have an additional step to get a cross section from your SEM or your FIP in order to fit into the model. So one of the things about about shale analysis is that you can find out what is the pore space by doing a technique called pyrolysis. You know what's pyrolysis? You just heat up the sample until you burn off all the oil, right? So after that, now you'll be able to see, okay, where are the organics? And then you can do your micro CT to scan where are the organics, so that those are the pores left over after the organics is burned off, and then you can calculate your porosity that way. So here in this case, you can see that as uh, the porosity of this shale at 20 degree is very little, nothing pass through. At 350 degree, also no porosity. But then as you start to pyrolyze this at let's say 380 degree, now you start to see cracks opening, then your porosity increases, and then 390 even more porosity, 400 degrees even more, and 420 degrees even more. So part of it is because the organics are now burnt off, and it may open up the pores that way. So there's another example here is you can also do a X-ray microscope to look at where are the kerogen rich region versus where are the silicate rich region. And then from there, after pyrolysis, now you'll be able to do your pore network analysis. So that will be one of the workflow you can do. So here is an example of a shale sample uh, that has been analyzed using the eclipse. So you can see that you can see all these bigger pores and also all these little tiny cracks, and also all these silicates or other minerals within the pore. So that will be the ability to look at the pore structures with a high enough resolution system. So here's another example where we are going to do a submicron imaging of a limestone. Here you have a limestone. So we image this at lower resolution. Now this lower resolution has the field of view is 2 millimeter. Over here, I can do a imaging at about 2 micron voxel. Then later you can also continue to zoom in at 0.6 4 micron resolution to get higher imaging quality. So that is one method. The other one is if you take a look at how you get all those digital rock physics or flow is this. You start off with the 3D image, then you do a virtual slice, right? Uh, so you can see that this is a CT slice, so you have pore space and so on. And also, you can also do a 3D modeling or 3D rendering, which shows you where are the solid phases. This means the software will be able to calculate all the solid phase within this carbonate. And after that, it can also subtract or calculate all the void spaces or the pore spaces. So once you have done this, you know what's a solid phase, you know what are the pore space, then you can use things like lattice Boltzmann and Darcy type of modeling to be able to get your pressure distribution or your velocity distribution. These things right now are available in terms of the different type of software packages. Right. So here is the example for the carbonate, where you can look at a zero point 0.3 to zero point 0.3 micron voxel. These are all submicron imaging, where you can now start to see the tiny cracks and the tiny pore space within the carbonate at the submicron resolution. So you can see your 3D and also you can see your 2D. So also you can use deep learning or AI to be able to study and
Sorry,
or
sir.
segment. Yes,
I have some question.
sure.
My name is Jonathan Christian from Lemigas.
Yes.
I want to ask about the kerogen part, yeah. Maybe 3 slide before this slide.
The Caribbean,
Uh,
this one,
no, previous one.
this one,
Again.
this one.
No, previous. In pyrolysis
That,
system.
oh, pyrolysis.
Yes. No, no,
This
no.
one is just the resolution, how resolution will affect your modeling. This
Uh,
one,
Next.
this one.
Yes, this one.
Yeah. Okay.
Uh, Maybe I miss the explanation before. I just want to ask about the paralysis system here. I want to ask that this this equipment can do paralysis analysis parallel with uh, the visual analysis like this one, or we do this analysis with the sample after uh, paralysis from geochemistry analysis.
Yeah, you have to do it with two different equipment.
Oh,
You have to scan it before pyrolysis,
okay, I see.
and then after that you go to your pyrolysis machine. You can take it out every so many degree,
Yep.
and then scan again, and then
Okay.
put it back, go higher degree, scan again.
So as I know, if we do a paralysis analysis in geochemistry lab, we do it by powder sample.
Yeah. In this
So
case, it's a rock sample.
okay, so it will we will use a different type of sample in this kind of analysis, yeah. If we do paralysis before, we do this analysis
Oh,
like
you use
this,
the same sample, except that this one you use a very small piece.
very small piece, but
Yeah.
just the origin rock, yeah.
Yeah, from the original rock. That means you sample, let's say you look at your shale, right? Using your microscope or whatever, you can see that,
Yeah.
okay, this is kerogen rich. Then you extract maybe 1 millimeter out of that.
Okay, I see.
Okay, and then
Okay, so
you, yeah. So this type of experiments you can do.
okay, I see.
Yeah, but then you will need to have high resolution.
Okay.
Yeah,
Okay, thank you, sir, for your
yeah.
explanation. Yeah,
Mm-hmm.
it's clear for me. Thank you.
Yeah, yeah, okay. So yeah, so this is how digital rock physics do, and also you can use other type of things in order to use deep learning to understand segmentation. This one is a kidney stone, where you can now look at different pore size and put color into it. All right, now let me show you. All right, when you are doing a rock, right, and then from there you can look at 8 microns. You scan for 8 microns, and then after that, you continue to progress scanning at a higher resolution. Like for instance, from 8 micron, I can scan all these things like what we have seen earlier, this 8 micron type of imaging from the slice. This is 3D. This is now the slice at 8 micron. Right. Then after that, you can resample again. Here, this means now you set your system without cutting the sample. You just go interior tomography. This means your X-ray microscope now focus on the tiny area at 1 micron. And then you will now get a image like this. And then after that, you can, after you got your 3D image, now you can do your slice. You can see that so much more details, right? So you can see that the mineral here, there are cracks here, the voids here, right? So therefore, using this type of data, you can do your prediction for your permeability. Now it's 1 micron, right? These are here you can see that you can see how clear is it. Are they very much like your SCM? Except that we did this non-destructively, and also we do not need to put in a coating, no need to be conductive. And this is we just do the whole rock, 5 millimeter or whatever millimeter, we can actually image this, right? So here you can see that scan at 1 micron, and also you can see the micro fractures over here within this particular rock. So that is the quality of a good X-ray microscope, right? Here is also 1 micron. You can see the micropores, right? So here you are looking at a 8 micron system. This thing is very spongy. I'm not sure what's a sample, but then you can actually see that. So now I want to show you that if you have the money, you might want to consider uh, using a bigger detector. Our standard detector is 3K by 2K, is 6.7 megapixel. And if you, let's say I can get a half a micron voxel with a field of view of 1 millimeter by 1 millimeter, let's say. But if I were to increase my detector pixel to 13 megapixel, now you may double your field of view. And if you were now to increase it another double of this one to become 27 megapixel, where 6K by 4.5K, we will be able to get a field of view that can cover the whole core. Like for example, if you have a rock core that is about 40 millimeter in diameter, I will be able to capture the whole thing without having to stitch. I can only capture one time. So therefore, if this is 80 millimeter, this means I have 40 and 40. I can capture 140. and another 40, and I can stitch the data set together. So now we would have a 80 by 40 millimeter, or even if it's 120 by 40, we will be able to capture it, and every field of view will give you a 9 micron resolution. And 9 micron resolution will give you this type of results. So this is a cut off section in 3D, and this is a 9 millimeter of a 40 millimeter diameter core, and we just capture once. But if you want, if you were to do, let's say 2 times divided by 6, 27 divided by 6 is, okay. If you were to do just a using the standard detector, you may have to stitch that at least 4 times on one side. So therefore, you may have to stitch many times to restructure the whole core. So that will be a large, ultra large detector that is available, especially if you want to capture large volume at high resolution. Okay, and like for example, like just now the sample we did 1.5 inch. It only took 2.5 hours, 2.4 hours, right? To do 3 scans. That means I think they stitched 3 samples, 3 regions together at 15 micron resolution. And then if you were to use a 27 pixel megapixel detector, if I were to use a 5 millimeter diameter, okay, I will be able to do that in with a field of view of 4 millimeter by 3 millimeter at 2 micron resolution. I can do that in 6 hours. Whereas if I were to use my standard detector that's 6 megapixel, and I'm going to do that at 0.3 micron resolution, it will take me 12 hours, right? So, and if I want to do even higher resolution, it will, a lot of this type of high resolution may take you an overnight run. This means before you leave for the day, you put it in and scan it, and tomorrow morning you collect your data. So therefore, what we can offer you is the choice of different detector type in order for you to have large field of view even at high resolution. So here's another example. If I have a 1 millimeter at point, this is a core about 1 millimeter at 0.25. Okay, 2 millimeter at 2 millimeter core at 0.25, and 5 millimeter at 0.3. So the image clarity across the sample size, right, from the diameter of 1 millimeter to 5 millimeter core, you can see that the clarity is still the same in terms of whether we use a bigger core or we use a smaller core size. So it is pretty comparable. In other words, what I'm saying is that I can do interior tomography. This means I can start with a 5 millimeter core and still get you submicron resolution without having to cut the sample. So that will be the power of this system. This is a 1 millimeter core sample where, because I think this is tight sense, so you can see that even when I'm doing a 0.25 micron resolution, you still have a the pores are still relatively small even at 0.25. But then you can still segment them and look out for the minerals as well as the pore size. All right. The next thing is, what is our resolution at large working distance, especially if you are looking at next time you want to do mechanical, you want to add a thermomechanical stage. When you add a thermomechanical stage here, like for instance, you have a tensile stage or a compression stage that has heating and cooling in it, you will see that your source and cannot go too near to your sample. But then the advantage of our system is this. We will be able to put the source 50 millimeter away from the sample. We can still get a resolution of a submicron, like 0.8 or 0.7 micron resolution. Even if I have a big stage, I'm not near my sample, I will still be able to get submicron resolution even at a large working distance. Many systems cannot do this. All right. And if you have a lot of samples to run, we also offer robotic handling where you can put many samples so that nobody needs to go there for the next day or so. You can run every sample, then only you go and deal with it. All right. So another advantage is our software, right? We have various type of software imaging, like for example, your data is very noisy. We can do iterative reconstruction, therefore the noise are gone, right? We can do phase contrast imaging, and also we can actually do a reconstruction of a 1K by 1K by 1K data set in just 4 seconds. And if I do a 2K by 2K by 2K, it's only 45 seconds, right? So next, we can also look at phase contrast and phase retrieval to take away the halo in the ring there so that you can now easy to segment. And here is another example of raw data. Raw data, it looks very nice to the eye, but when you want to segment this, you find that it will start to segment through all these lines and striation. So therefore, it is going to be very difficult to segment. So using phase retrieval, you can get rid of all those lines so that when the computer segment, you know that this one is one object and not many, many different objects. All right. So that's the overview of what our system can do. So I'm open to questions.
All right. Thank you very much, Mr. Law, for the presentation. Yeah, it's really interesting. Anybody from Lemigas have some questions? Maybe Bu Pertiwi or Bapak Jonathan Christian.
Maybe I have one question.
Yes. Yeah.
Thank you for the presentation. We can now understand how this eclipse works. So one of my questions is using the like a very small or submicron spot size source, what effects will we get on the source that will limit the analysis?
Okay, the source doesn't limit analysis because it's very bright as well.
Mm-hmm.
So typically you can run it for big samples or small samples, it doesn't matter using our source.
Okay.
So there is no limitations in the small spot size of the source.
Okay. So what makes it different with the other
Yeah,
source?
because the difference is one of it is that it is very bright. This
Mm-hmm.
other thing is that it is an open source. In other words, your cost of ownership is going to be very much reduced because generally your source is like a light bulb.
Mm-hmm.
In the light bulb, you have the filament, right? So if let's say if your source is like a bulb everything is sealed, your vacuum is all inside. If anything goes wrong with your filament, what will happen to your light bulb? You have to throw it away, right?
Yeah.
And buy a new one. So an X-ray source is also like this. If your X-ray source is a closed tube, meaning all your filament and your target is all inside the sealed tube.
Yeah.
If one of them is not working, what will happen?
Change all.
You have to change the whole thing, right?
Yeah.
So using our source with the new technology, it is an open source. That means the vacuum pump is pumped separately, so that if, let's say, in the event I need to change the filament, I can stop the vacuum and open it up and change it.
Okay.
So therefore, your cost of ownership drastically goes down. And also, how often do you have to change? Some people or some vendors, they have a X-ray source that are open tube, but you have to change every 300 hours. That means you spend a lot of time changing, and
Yeah.
it's going to be very costly. But ours will take you about 4,000 hours, which is very close to what the closed source will guarantee you. A closed source tube like from Zeiss will guarantee you 5,000 hours. Ours, you just need to change the filament maybe every 4,000 hours. So
Okay.
therefore, in terms of technology, it is very much advanced, and also it saves the customer a lot of money.
Can the operator change it by themselves, or like we need to contact the professional from the Sigray
Oh,
to change the
no, you
filament?
can change. You can have Aris and his team to come and change for you all.
Okay.
They
Yeah.
will be trained on how to do that. Or if you want to change it yourself, then you just get training on how to do that.
So one
Okay.
more questions. Like
Yeah.
for the software, if we
Yeah.
want to like analyze the software, like the your last few slides, uh, can we do that like in the same computer with the same software, or like need to be installed in the different computer and different software?
You can do it in the computer, but it's more productive if you have a separate workstation, isn't it?
Okay. Yeah,
Yeah,
yeah.
because then you cannot do your work. You have to go and sit in the lab to do your analysis.
Is
You
it only
cannot
like
do.
one computer, one license, or we can like have?
Yeah, yeah. There's one computer, one license, yes, but then we can make some deals for you all if you want a separate workstation.
Thank you, Mr. La.
Yeah, and also a lot of times some people actually go home and do their work, depending on whether you allow internet to access your server.
So the software can like access the internet.
Yeah, you can do that.
Okay, okay, cool. Yeah, thank you.
So are you also consider a government or you are can you be considered a research institution?
We are previously a research institution, but now we have like different ministry to do the research and innovation. So like we're switching to the service.
Or
Service.
treating the service? Yeah,
Yeah.
in that case, then you cannot get free software.
Oh, so it's only like for research institution.
Yeah, research institution, I think you can get some free software for the Dragonfly reconstruction software is free for academics.
Mm, okay.
Otherwise, it is yeah, there's a quotation for it. Depends on what you want. So you do a lot of permeability on SEM
Just like the visual porosity, like the
porosity. Yeah, okay. Yeah, that is 2D. So now with the CT, you will be running it at 3D. and therefore you have different set of software. That one you may need to go for training, or you may have to collaborate with some other people in Indonesia who are expert in that.
Mr. Lau, can I have a few questions, please?
Sure.
Okay. My name is Adrian. I am a petrographer, and before I want to explain to you something, beside for shale analysis, we have overview for this microcity for formation damage in sandstone reservoir. So basically,
Yes.
we have 1.5 inch core plug samples of sandstone,
Mm-hmm. Yeah.
and we'd like to know the effect of fluid injection on that core on before injection and after the injection, and then we compare it uh, to see the difference or the damage of the injection to the rock. We usually not using microcity. We usually use petrography, SEM, XRD, and also MICP. And in
Mm-hmm.
MICP, we mostly see a, a change of arrangement of pore distribution, pore size distribution in the range of 10 micron to 100 micron.
Yeah.
Mostly the pore that has a significant effect on the permeability of the reservoir.
Mm-hmm. Yeah.
So in your explanation, I can highlight that one of the edge of the microcity is in undestructive analysis. So we can analysis the before, and then we do experiment with injection, and then we analyze it after. But
Yes.
regarding the trade-off between field of view and resolution, that as I mentioned before, we need to see the 10 micrometer, 10 micron structure of the pore, and of course we will not have the time to spend with to analyze all the sample. We have to limit the sample to gain optimum time for analysis in this microcity. So my question is this: what are your advice? Can we analyze the core sample in the exact same position on the core? The coverage of the core, we may not be able to cover the all area. Can we can we analysis on before and after on the core in the exact same position, so uh, we can compare the result exactly same position but with different parameters, or we just need to extract the data like for distribution, like connectivity in the slightly different position, and then compare it using the derived data from the rock physics modeling. Thank you, sir.
Okay, to answer your question, if you have a 1.5 inch core, like I shown you in the presentation, if you can afford it, I will recommend that you get the 27 megapixel detector, so that the full field of view is over 40 millimeter, which is bigger than your 1.5
Okay.
inch core. So that means you capture one time. Right. So
Oh.
so therefore you don't have to stitch many places, because let's say if you want to do 10 micron, possibly your field of view may be only a few millimeter. Not it's
Hmm.
not going to be 40 millimeter. Possibly at 10 micron, your field of view with the standard detector might be around uh, 10 to 20 millimeter, maybe 10 to 20 millimeter at the most. Okay, then you may have
Basically, half the sample, we can cover half the sample, right? With
you
10
can do
10
sample,
micron.
but then your flow is gone already. Or
Okay.
you can stitch, and you can scan here and scan there and scan there and stitch together. But then if
It's
you do not want to spend so much time, you just
yes.
do the big detector one shot, you can take everything. You can also do
Okay.
higher resolution too.
Okay.
using the large detector. So that will be one recommendation. All depends on your budget. If not, then instead of getting the 27 megapixel, you may get the 13, is the intermediate rather than the smaller detector. The in between one also will give you twice the field of view. That will also give you useful information. And the other question is that, okay, how do you get back to the same place? So there's what we
Yeah.
do, what you call fiduciary. This means in your first scan, we will look at, okay, what are some of the characteristic marker there? At the top, at the bottom, or the center, or you have to specifically mark it physically, right, in the corners of somewhere, so that later when you put it back, it will be aligned according to those markers.
So, is there any fine-tuning feature in the software that we can match the two models rock
Yeah,
physics
you
together?
can you can match them electronically. That's how we stitch. Means we
Okay,
have
yeah, I get
one
it, I
and
get it.
here, and then you have to overlap them, and then make sure that the pores and the grain are now evenly matched. Then we
Okay,
start to say that, okay, we stitch it from here.
okay, thank you, sir.